Let's look at alpha decay. Now, the beautiful thing about alpha decay is that it's just a spontaneous nuclear reaction. So if you already know how to find Q value, then you know how to find the Q value for this, okay? In fact, if the mass of the right side is not less than the left side, then the decay just doesn't happen, okay? So let's look at this thing, right? We need to know this. We need to be able to remember that an alpha particle we're going to represent with a helium, okay? So this is what uranium-232, thorium-228. This is an alpha decay, so it'll decay to this. Notice that this mass number goes down by 4. The atomic number goes down by 2. This is exactly what a alpha decay does, right? And so the first thing we're going to do is we're going to look these masses up in the table. So you're going to look this up, okay? So this, you look up uranium-232. There's the mass. Look up thorium-228, and you'll use your reference guide. Okay, so look those up in your reference. Okay, and don't, if you're a spaz like me, write them down carefully. Okay, and then basically we're just going to look at the mass of the left side. The mass of the left side simply is 232.037131. Okay, the mass of the right side, we have to add these two together. So 228.028716. 028. Okay, plus 4.002603. And I think our textbook has this number as a 2. Okay, so they've refined this in the last 20 years or something. They've refined this. So the whole left side is 232.031319. Now, if you're paying careful attention, you'll notice that the right side has less mass. Look at that. This has got a 7 there. This has got a 1 there. Okay, everything else is the same, right? It's like everything before that is the same. So if we subtract that, we can get something called the mass defect. And this is only a defect if you believe that mass is conserved. We understand that mass can be turned into energy, right? So I'm going to go 232.037131 minus the answer I just got. And our mass defect is 0.005812. Okay? This is mass that's been converted to energy. Okay? What we say is that it's the energy of this decay. Okay? And to convert that, to turn it into MEV, okay, 1 U, if you turn one atomic mass unit into MEVs, it's 931.5 million electron volts of energy. If we're using the formula E equals mc squared, okay, and then we're just converting it to electron volts. Okay, so turn that into kilograms, put it in there, put the speed of light in there. Don't round anything either. Use really accurate values. Turn this into electron volts, divide by 1,000,000. You'll get this number. Okay, so we're going to use that. So basically, if we're turning this to MEVs, we're going to go 0.005812 U times 931.5 MeV. There's a decimal point there. And that's MeV per U is what that means, right? So times 931.5, it's a very long way. Some kid was from another school was looking at this video, or one of these videos, and he goes, you just multiply by 931.5 at the end of the video, but you don't explain why. Well, that's because you're seeing like the last whiteboard problem. Okay, so I'm getting 5.41341. How many sig figs? We have 4 sig figs, so 414 is what I would say, MeV. So this is the energy of this decay, okay? In general, it's believed that the alpha particle carries this away as kinetic energy. So you have the parent atom, right? And then you have the daughter nucleus. It's always a daughter, right? Okay, and then the alpha particle. Generally, this guy has to recoil, but it's got so much more mass that it's going to be going very slowly compared to this. So this guy will carry away a bulk of the kinetic energy, but obviously not all, because this has to recoil this way, right? Okay, so anyway, there you go. We'll just pretend that the alpha particle has all that energy. Now, the question is, why does alpha decay occur? And the only way it can occur is if by doing alpha decay, we decrease the mass. Okay, or by the way, we're increasing the binding energy, decreasing the mass. We're going to a more stable configuration. Okay, and we do that because if you look at the this whole thing there, right? The helium nucleus of these small nuclei is actually one of the more tightly bound ones. You never ever see atoms pitching off in normal situations. We don't see any decays where they pitch off a proton, right? Because this requires a lot of input of energy, right? This guy's fairly tightly bound, so it's possible to barf it out and reduce the mass of the nucleus. Okay, so it all has to do with the mass. It has to do with reducing the potential energy. We reduce the potential energy of the nucleus. That's the thing to remember. Okay. Yeah. So that's why alpha decay occurs, is to just reduce potential energy. And if it doesn't reduce the potential energy, if it increases it, that alpha decay doesn't occur.